So we've already looked at the basic gas laws and where they've come from, but then people wanted to combine them together and they wanted to make them more ideal. Now, me saying that gases are going to behave ideally is like saying life is going to behave ideally. It's just not true. But for the sake of this class and for the sake of simplicity, we're going to pretend that gases are well-behaved little atoms and that they are going to be listen to every single one of those kinetic molecular theory laws that we looked at previously. So when we're doing it, that means that all of these atoms are going to follow these simple equations that you see here, where the top is the combined gas law because it combines Boyle's laws, Charles' law, and Guy-Lussac's laws. Here, this is the ideal gas law, where we can say, hey, if we've got some magic constant of R, maybe we can relate pressure and volume and moles and temperature all together in one pretty little equation. And then this last one is, hey, if we've got standard temperature and pressure, I know the volume of any 1 mole of any gas, and that is 22.4. So we get to use that like a conversion factor. So with this video, I want to break apart these new gas laws, that of the ideal gas law, and then also this 1 mole at STP. And we're going to look at those a little bit closer, and then we're going to do some practice problems that use the combined gas law or the ideal gas law. So standard temperature and pressure, what are those values? Standard temperature just assumes 0 degrees Celsius, which is 273.15 Kelvin. Standard pressure is assumed to be 1 atmosphere, or 101.3 kilopascals. So just like when we're converting from grams to moles to molecules, etc., you can convert all of these units. So it just depends on how you want to express it. Physicists might express it one way, engineers another, chemists another. It just really depends. It's the same way as here in the United States, we report our temperature using the Fahrenheit scale, whereas in Europe, for instance, they might use Celsius. And so it's just a matter of looking at the units in it from a different vantage point. But all in all, this rule states that any 1 mole of any gas at standard temperature and pressure is always 22.4. So your problems might look something like, hey, you've got 2 moles. What's the volume? You could use the ideal gas law using each of these parameters where for temperature you plug in 273.15, for pressure you put in 1 atmosphere, or you could just note that if the gas is at STP, it's 22.4 liters per mole. So 2 moles would be 44.8 liters. All right, so within the ideal gas law, PV equals nRT, there's this new gas constant of the R. Now, for the most part in this unit, we're going to be using R as 0.0821 liters times atmosphere per mole K, and that's because these are the units that are most likely used in the gas constant. In the gas equations, the gas laws. Do notice that this is a K for Kelvin, and so you cannot use Celsius when you're putting your temperatures into this equation. You must use Kelvin. These other R values are important. It just depends on your vantage point and how you're using it. So for this unit, for gas laws, ignore all the other R's. Just focus in on this R, that R equals 0.0821. Some more units you want to consider is pressure. So pressure is defined here as the height of the column of mercury that you see in millimeters. That's where the unit millimeters of mercury goes, is if you have a column of mercury, then the pressure downward will change the height of the column. And so there are different ways. You can have different barometers that measure it very similarly, but all in all, there's a lot of potential units for pressure. Here you can see all the other units for them. 1 atmosphere, 760 millimeters of mercury, and 760 torr are the ones that you will see most commonly in this course. But there are others depending on how you're using pressure. So newtons, pascals, typically those will be used in physics. But they're all just different ways of expressing the same thing, which is force per unit area. When we're talking about chemistry and gases, that's going to be force per unit area that we're talking about on the outside walls of that container. With that, we have looked at all of them now, even if it's ever so slightly. So with the ideal gas laws, it's PV equals nRT, combined gas laws, and then each of the individual gas laws. Avogadro's law, we didn't really talk about much, but basically it's relating volume to moles. But they're all very similar, whereas if you combine them, you get this combined gas law. I've even seen moles included in the combined gas law, where N is down here with the temperature. So that being said, anytime you have a problem and it looks something like this, the how you do these problems is very systematic. You identify your variables, which is what you have, you can see here on the left hand side. So this problem says a scuba diver is initially at 1 atmosphere and submerges under the water to a new pressure of 3 atmospheres. Their lungs originally held 6 liters of water. If they held their breath as they submerged, which FYI is very bad, we talked about that earlier, what would be the size of their lungs at this new depth? So let's identify the variables, meaning we have 1 atmosphere. You have to decide, is that a pressure? Is that a volume? Is that a temperature? What is it? That's a pressure, and we know that because of its units being atmospheres. So this is your first pressure. 3 atmospheres is your second pressure. So I identify that as P1 and P2. And then they originally held 6 liters of air. So that's V1. It was original. Then what is the size of their lungs at this new depth? This tells me I'm going to be searching for a V2. So if we look back at this table and we ask ourselves, which of these equations have a pressure and a volume and nothing else? Everything else is held constant. I hope you zeroed in on this top one here, Boyle's law. Pressure times volume equals pressure times volume. And now it's just a matter of plugging in the variables into the equation. But if you don't first define the variables, you're going to be staring at that list of equations and having no idea which one to use. So I say identify the variables and then just use whichever equation makes sense. And it makes sense if it only has those variables and nothing else. All right, so we plug in the values. 1 times 6 equals 3 times my new V2. Now in order to get the 3 to the other side, I need to divide, so this will look like 1 times 6 divided by 3 to give me a V2 of 2 liters. For our next problem, we are asked, if I have 75.9 moles of a gas held at a pressure of 5 atmospheres in a container with 50 liters, what is the temperature of the gas? I want you to stop the video right here and try and identify the variables. If you identify the variables, what you should have gotten is your moles, your N equals 75.9, your pressure, P, is 5 atmospheres, and your volume is 50 liters. And then it asks you for the temperature. So I always put T equals question mark. Now you might have started putting subscripts like N1, P1, V1. If when you get to the end and you only have 1s and you have no 2s, just erase all your 1s. It's okay. That kind of tells you that you probably are going to work with something like PV equals nRT, because this equation has everything we've got and nothing else except for that pesky r. So what do we do with the r? This is a new variable that was not defined in the problem, but you have to define based on your knowledge of this equation. And so your r equals 0.0821 liters times atmospheres per mole K. So now that you know all of these variables, you can plug them in and you can solve for your temperature. So by doing this, you'll take your N and your R, divide both sides by N and R, which makes it be PV divided by NR equals T. And then you plug that in your calculator, making sure you go 5 times 50 divided by 75.9, enter, divided by 0.0821. That's how I do it, just to make sure that you are using order of operations correctly. And you get a final temperature of 40 Kelvin. Notice I do have my units in Kelvin. Why is that? And that's because your R has units of Kelvin. All right, if it doesn't ask you, change that temperature to Celsius or something like that, if it said that, you'd have to convert this back to Celsius. But if it doesn't say that, that answer is perfectly fine. Our next problem states a 550 milliliter sample of nitrogen gas is warmed from 77 degrees Celsius to 101 degrees Celsius. Find its new volume if the pressure remains constant. So stop the video and identify your variables. You should have found that the initial volume is 550 milliliters, which is equal to 0.55 liters. Then temperature 1 is 77 degrees Celsius, temperature 2 is 101 degrees Celsius, and volume 2 is unknown. That's what we're trying to find. So this means that you should have used V over T equals V over T. And then you can just plug in all your variables and solve, right? No, I hope you caught the big problem with that. You can't use degrees Celsius in gas law problems. You have to first convert your temperatures to Kelvin. And Kelvin is degrees Celsius plus 273. Therefore, temperature 1 is 350, temperature 2 is 374. Now you can plug those into this equation. and then solve to get a new volume of 0.588 liters. And does that make sense? If you're going to increase the temperature, do I expect my gas to expand? Absolutely.